Okay, so welcome to today's webinar. Today we're going to be talking about industrial fan systems and in particular taking effective system measurements. Now we've actually also included a case study today of a HVAC system which will obviously have applications further than just your traditional sort of process air application. So without any further ado, we're just going to quick overview of what we're going to talk about today, just sort of a quick review of our fan system, how we define it, understanding the demand side of our system in terms of what we're going to be looking to measure, flow rates, temperatures, humidities, pressures, and how that's going to be useful. Then understanding obviously the supply side of the system, and then we're going to use a couple of case studies. So just a quick reminder here, we don't want to take too much time today, but reminding that when we have our fan system, it's a lot more than just the fan, filtration, and obviously actually where the air is being used, whether it's for a sort of environmental need in terms of HVAC or just ventilation, or it could be actually a process requirement. So in all these cases, you know, it becomes a question of where we draw the boundary, and we'll sort of talk a little bit about that. But a key question that we're going to be continually coming back to today is, where do we draw the boundary? So once again, we've used this analogy before. I'm not going to take too much time. It's in here just as a reminder that our demand side of the system is where our gas, typically it is air, is being used, whether it's for heating, cooling, etc. Obviously how we get it there through various ductwork, dampers, isolation points. Then on the supply side we obviously have our fan system, and just a reminder of course that we want to understand what the system's actually doing before we worry about the fan itself. Okay, so the key point to remember as we go through today, and this is really just a very quick way to get started today, just to remind us to set the boundary conditions of what we're trying to do, and that is we want to focus on the total system, i.e. use a systems approach and not just the fan itself and its efficiency, because we could have an incredibly efficient fan, but if the system it's driving isn't right, then it almost doesn't matter the efficiency of the fan. Okay, and so obviously it comes back to, well, what is the airflow or gas flow that you're dealing with? Sort of cooling system, heating system is some sort of process input flow. Could be a HVAC system where you're trying to control a pressure or so many air changes per hour, etc. There's a number of things that you could be trying to do, and it's important to understand what you need to do as opposed to, well, I just want the fan to run efficiently. So it's taking a much bigger picture. So obviously getting started, before you even begin to take measurements, we need to think about, well, what is the actual system? And so we're going to start by compiling some baseline data. So obviously you're going to start, you'll have some fan and motor nameplate data, you'll have a sense of operational hours, understanding what the purpose and function of the system is. Then you'll be looking to collect various P&ID drawings or process and instrumentation drawings for those not familiar with the terminology, understand the control system, identify the actual true cost of running the system. Now that's going to of course be your energy costs, it's also going to be your maintenance costs, and understanding what those true fully loaded costs on the system are. Then we need to identify, and what we say we identify is we've got to identify, are there any other critical system components? You know, we've got, you might have your fan, but then what are the other critical elements that we need to be worrying about? What are the existing meters that we have in place to give us data? And then what sort of access points do we have to make measurements? Now, if it's a regular sort of ambient system, then putting your probe for measuring velocities or flow in and out of a duct can be relatively straightforward. Likewise taking pressure measurements. However, if the system is being run under vacuum or under pressure, or has got some rather interesting chemical compositions, you need to perhaps be careful. There might be some health and safety precautions that need to take. So there's some critical things that you need to be mindful of to make sure that you're not going to put yourself or your equipment in harm's way. So one of the key things, and we'll mention a couple more times today, is you've got to be mindful of your equipment will be rated to certain temperatures and certain qualities of the air. So you do need to be careful to make sure that you're not putting your equipment into an application where you're going to destroy or ruin it. Okay, so that being said, once you start looking at, okay, getting started and you've assessed the system and you're starting to think about, okay, well, what are we going to measure? Well, the reality is there's a number of different audit standards you can point to. There is a fan system specific standard that was developed here in association with ECA for ECA Energy Auditors around fan systems, and that's available from the ECA website and the EMANS website. And in that is some guidelines around measuring or metering electricity pressure, flows, temperatures, humidities. It was all covered there. Now there are some very useful broader ANZS standards around measuring pressures and flows in HVAC applications and the like that generally, in my experience, can be difficult to apply in industrial settings. However, you can at least take the guidance of that standard as a document to help you determine what you will and can't do. There will be additional application-specific standards that you might be able to reference depending on the industry and application you're dealing with. But the key points to take home here is, of course, the fact that you need to think about what is the purpose of my measurement, what sort of accuracy do I require, and what sort of sample frequency do I need to take to ensure that I capture relevant data without sort of inundating myself with a whole heap of plant noise. So that being said, we need to be careful that we don't measure too much and absolutely get swamped with data, but equally we need to make sure we are capturing the whole system. And so obviously one of the things to be careful of there is you may also need to take additional measurements of other associated process variables in terms of the performance and function of the process that the system is driving or is attached to. Now, just very quickly, we're going to talk today, or just a refresher really here, of flow measurement. When do we want to measure it? Where do we need to measure it? And how are we going to measure it? And so we've got a couple of scenarios here. We could look at the fan inlet, we could look at the fan exit, we can look at individual end uses. We need to be very careful as to where we place the meters. Now, as to the how, well, that all actually comes back to, well, the needed accuracy and also the application-specific limitations in terms of pressures, temperatures, and the composition of the stream that you need to measure. Now, the other thing, of course, you need to do is understand the system and its function. So, as we said, you might need to take a few more measurements, understanding and capturing your demand profile fully. Is the system currently run with a VSD, or perhaps will it need a VSD? Are there alternatives to controlling and sizing the system? Is the flow actually fairly steady, or is it varying a lot? Understand what it is that you need to capture. Now, this is a very quick refresher for today, but it is important to remind ourselves that when we're measuring turbulent flow, the more accurate measurements are going to be in a straight section of duct. Okay, so you're going to get a turbulent profile, but we need to get a uniform profile. So as an ideal best practice measurement, if you're doing a laboratory controlled measurement, you actually want the best part of 30 duct diameters, 20 upstream and 10 downstream. Now, in the real world, it's normally quite a challenge to get that. And so what we tend to do, as shown here in this illustration, is you really ideally want sort of 10 to 15 straight diameters an absolute minimum. And of course, what you're then looking for is sort of a 2/3, 1/3. So you want 2/3 upstream, 2/3 downstream. As you can see, around elbows and valves or other actuators in the duct, or flow dampers if you like, you'll get a disturbance in the flow. And sort of you look at the peak velocity distribution as you see there of the two cross sections. We obviously need to be very careful with the point on the left there. You can end up getting it horribly wrong. You might get lucky and get it roughly right, but the potential error is significant. So you do need to think very carefully about where you're going to take your measurements. Now, I have actually shown this slide previously in another webinar, And so we want to just recap very quickly here. And this is, here's a fan. It's an open inlet. You've got an outlet here coming through some duct, round a bend, and then we've done multiple measurements. And so one, obviously at the fan intake, the rotary vane anemometer. Two, at the fan outlet, then further downstream in the duct at point 3. 4, after the bend. 5, further downstream, and then 6 at the actual outlet. Now what you can see here is these are the measurements based on those 6 points. And what I want to talk about very briefly, of course, is why is number 1 undershooting what the actual flow is. And what you'll realize, of course, is it's very difficult to capture an open inlet, especially at a fan inlet, because the flow is accelerating. It's very difficult to get a accurate measure, and generally you will under predict. Now, interestingly, at the fan outlet, rather than under predicting, we're over predicting. And so we want to talk just very briefly today about understanding why. And the reason for this over prediction on point 2, of course, is after the fan, we've still got a relatively high dynamic head that's been generated by the fan. And we'll talk about that in a little bit more detail today. And of course, what that then translates to is we have a lot of in-plane velocity components, which means that our velocity magnitude at that point is higher, but that's not the true axial flow rate of air through the duct. And so we tend to get our actual velocity measurement gets contaminated with, I guess, put it down to the turbulence after the fan. The flow hasn't settled down, and so we end up contaminating our true, genuine axial velocity, which of course is our flow rate, with in-plane velocity vector components, which mean that we will typically overestimate our velocity, and depending on the nature of the system and the nature of the fan profile, that can be significant or not as significant. In this particular case, the error was almost 100%, so it was nearly double the true flow rate. So you've got to be very careful. The only other point I'll make here with regards to point 6 is, once again, at a free outlet, it's very difficult to fully capture the flow as well. Okay, so in summary, when we have non-uniform flow, it's very important that you have to be somewhat suspect of your flow measurement. You're going to have a challenge in terms of repeatability. You're then going to have a challenge in terms of your sample time, how many samples you take. You're going to have to literally swamp yourself with statistics to get a rough sort of average flow. Now, if your flow was non-uniform as well as changing, you're going to have a real challenge on your hands. And so this is where you might need to use the alternative methods at the bottom of the page here. Now, if you have similarly with unconfined flows, once again, you will generally under-predict the flow, and you want to avoid that sort of measurement. If it's the only way you can get a measurement, you've got to realize that you need to put a significant error bar on your measurements. Okay, now that being said, you might be better placed to look at some alternative flow measurement methods, and that's back to process data, energy balances across heat exchangers. It could be a mass balance across a dryer, sort of say, for example, a water evaporation test or something along those lines. Okay, so just to give you an idea, you can look up various flow standards, and this is a couple of indications as you go with smaller ducts on the left versus larger ducts. You've got a sample tree, if you like, or number of points that you would take, and so you can see that you're sort of getting a cross-section of the round duct. There's similar charts available for rectangular and square ducts. Now what you'll find, those of you that have annubars that run across these process air ducts, what you'll find typically is they'll come across the duct at an angle, and you'll typically find for a larger duct you'll have 3 holes on the extremities out here and then up here as well, kind of mirroring 1, 2 and 3, and then 4, 5 and 6. But whereas you've got 2 here, if you're wanting to be super accurate, you could have 2 annubars perpendicular to one another. Most installations tend to compromise and have one just across the duct at an angle. and people sometimes don't even bother with doing that, and they just either do vertically or horizontally, which in the grand scheme of things, depending on the nature of your upstream flow condition, that's probably adequate. And so what you'll find is that you'll get an approximation. So that's all part of the providers that provide those annubars. That's all set up as part of their standard reference points for that annubar, and so that'll all be derived, and you'll get a measurement across those multiple points, and typically the annubar is an aggregator of those, and then you'll get a pressure differential which corresponds to a velocity, which based on your duct dynamics, a volume flow rate. Now, if you're going to be really careful, you'll then also look to do a temperature or density correction on that data. Now, just as a quick review today, once again, if we look at flow measurement, there's a couple of different pieces of equipment that we might like to use. And this is, first of all, the pitot tube, and just a couple of key points here. It can be useful for high velocities, not very good for low velocities, useful obviously for high temperatures. However, you need to be very careful if the pitot tube isn't aligned with the flow. You can get significant errors, and obviously the key point there is you need to understand the nature of the gas in terms of density, chemical composition, if you're going to then convert what is effectively a total pressure minus static pressure to give you your dynamic pressure, which is obviously then a function of velocity. However, you need to know density and obviously the composition of the gas ideally to understand how to make that correction. In an industrial setting, obviously, if you commission a supplier to put this in, they'll be able to do all of that for you as part of setting the instrument up. Now, a thermal anemometer or a hot wire can be very good at low velocities. It tends to max out sort of 50 meters a second or more, depending on the supplier. You might be able to get a specialty unit. Generally, they'll be a lot more expensive. And once again, generally they'll have a temperature limit. You can get high temperature thermal mass flow meters, which is another form of this type of equipment. However, obviously they need to be custom for specific applications as well. A key point with these meters is they tend to handle angled flows reasonably well. However, what you do need to understand is your velocity vector components that are typically involved, and if you're trying to measure a flow rate across the duct in terms of an axial velocity, you're wanting the axial component, which then becomes a problem because the meter, obviously a typical standard meter, is not going to differentiate. You can, however, get very accurate and expensive multi-component or 3D hot wire anemometers. Obviously they tend to be more for a laboratory setting, quite expensive and generally quite sensitive and need to be taken care of very well. So it's more about understanding the limitations of the equipment that you've got at your disposal. Obviously also particle laden flows can be a challenge, usually more expensive than a pitot meter. Rotary vane anemometers, there's plenty of good units on the market nowadays that can do this. Typically also you've got a velocity limit. Angled flows can be a challenge, obviously, because you need to get your vane aligned. One of the advantages, of course, with these is if you are looking for a axial velocity component, it will tend to give you a better representation of that. However, it will still have challenges if you've got highly angled flows. You'll get disturbances and it won't necessarily be a good clean sample. So obviously useful, a little bit more expensive again than a typical pitot tube, but generally these can be a lot more sophisticated, and some of the ones on the market nowadays also have a temperature compensation and sort of mass flow functions built in. Now with temperature and humidity, it's important that you understand the range of temperature that you're looking for, so you've got the right thermocouple or infrared if you're using it. Need to be very careful in terms of your surface emissivity. RTDs might be better accuracy, they're going to have a longer response time. So yeah, once again it comes back to what the dynamics of the system is as to how you can use it. Obviously if you've got a process stream, you might need to be careful about sheathing those transducers. Obviously with humidity you might need to be very careful with your sample trees and purge air gas to be able to take a consistent sample, and obviously particle laden flows can become a problem. They will destroy very quickly your humidity probe. Okay, so the main thing we're going to focus on today in terms of effective measurements is actually going to be pressure. This is probably your single biggest indicator of what's going on in your system and what you might need to do. Generally your system is going to be flow controlled or sort of outcome orientated, which will be tied to flow, and of course pressure is our single biggest indicator and our single best indicator of what's going on in the system. And so obviously we need to understand what's happening at the fan inlet and obviously the discharge, but then obviously also understand the system pressure drops, or where the actual demand is. Now of course there'll be two components to your system pressure drop. One will be what you actually need, then of course the rest will be your distribution in terms of getting the air or gas stream from where you need it through its various process unit operations and then out, and whether it's being recycled or vented. There'll be different number of obviously combinations and permutations as to how a system might look. You've then got of course your parasitic losses, your frictional losses, entrance exit losses that all build up to your total system drop, or system pressure drop. Now we talked about this in a previous webinar where we talked about system curves and fan curves, but what we just want to remind ourselves again is how accurate are our measurements, what's the limitation of our equipment. Okay, and obviously once again reminding ourselves we need to understand our system and its function. Now with pressure measurement we can use a static pitot tube, which is effectively what we're showing there on the side. So our first one on the left down the bottom here is obviously just going into the side of the duct, which is our static pressure of the flow going past. Our second one is our stagnation or total pressure. This is where the tube is open, directed into the flow, which is effectively what the tip of our pitot tube is going to measure. And then of course if you reference that against the static pressure on the side of the duct, then that actually then gives us our dynamic pressure, which is effectively the function of a pitot tube. So these are normally quite easy to do. Wall static pressure traps can be useful, and a U-tube might be quite simple, but generally these days you can get an electronic DP device where you can measure that pressure. You can log it, you can go from point to point and get very quick. It means you don't have to worry about losing fluid out of your U-tube. Is your U-tube big enough, and lining up millimeter scales to get your heights and all the rest of it. You don't need to worry about changing fluids for different pressure ranges. And if you've got limitations in your pressure ranges, you can get multiple DP cells with a range of pressure bands to meet what you need. Now we just want to take a minute just to go back. It's a little bit of a flash from the past for us, for many of us I'm sure, in terms of Bernoulli's equation. Assuming of course we have no change in height, our total pressure is obviously our static pressure plus our dynamic pressure. And in a system, obviously, those things are conserved. Excuse me. However, obviously, as you lose static pressure through parasitic losses, our total pressure is going to reduce. But then that is offset. Somewhere in our system, we'll have our fan adding in effectively static pressure by virtue of its work that it applies to the flow stream. Now of course static pressure is defined specifically as the pressure of the stationary fluid, and then the dynamic pressure is the kinetic energy per unit volume of the moving fluid, and most of us will be familiar with that being half rho v squared, rho being density and v obviously the velocity. Now you'll notice that that's going to change with temperature, obviously as density of whatever gas we're using is going to change. Now a reminder here that the velocity of course is a vector quantity having both a magnitude and a direction, and so in a duct flow this becomes relevant because our velocity that we're actually interested in terms of our flow rate is our axial velocity, and everything else in the other two directions or our in-plane velocities become part of our losses unless we can convert that dynamic head over into static head and ultimately this is where our system effects and losses come into the picture. Now, of course, with our fan, we're actually generating quite a bit of dynamic pressure in our fan, i.e. accelerating the flow as it goes through the fan impeller, and so we're actually generating velocity. And the idea of the fan and the fan housing is to design that so that that dynamic pressure is maintained to give us the flow we need, but then obviously the excess dynamic pressure generated by the fan then ultimately gets recovered, or part of it gets recovered to generate the static pressure that we require. So depending on how well we control the expansion of our gas stream after our fan is going to determine how much of that dynamic head gets converted to static head, if you like, as opposed to gets lost in inefficiencies and turbulence, if you like, in terms of the eddy dissipation as the flow tumbles down the duct. So if we have a poor duct design and a poor layout, we're going to have high losses and low static pressure recovery. Okay, so on that note, as we're talking about Bernoulli, we want to just cover very briefly today an understanding that you have reference pressures. And so whenever you're taking a pressure, you're referencing it to your localized pressure. Now, there are times where instead of referencing your pressure to your ambient outside or just next to your duct, you might actually have to measure an absolute pressure. Now, if you do this, you need to be very careful, especially in larger plants with multiple levels. And here's a really good example. So if you've got a 50-meter tall building, like a sort of a modern dairy plant as an example, or other process facilities, and you're actually using an absolute pressure measurement, okay, what you need to understand is, irrespective of what's going on with the process, just by virtue of gravity, we have a change in pressure with height. Now, to give you a sense of the scale here, if we take our 50-meter building at the ground level as opposed to the top of the building, our difference in pressure is our difference in height, which is 50 meters. We're going to times that by gravity, or acceleration due to gravity, 9.81 meters per second squared, and times by our density. If we just take a standard ambient density for air of about 1.15 kilograms per cubic meter, we end up with a pressure variation across the height of our building of 564 pascals. Now, that can be substantial. So if you're using absolute pressure as a reference, and that's the meter you have, you need to be very, very careful that you understand how pressure is changing in the background, i.e. in terms of your height. And so you'll then need to compensate your measurements accordingly. Now, if you have access limitations, we similarly have to apply Bernoulli's equation to correct pressure measurements. So, as an example, if we consider an inlet filter bank before of a process air fan, so we might have an access point immediately after the filter bank, which is quite typical, and the velocity at this point might be 2 meters a second. Whereas at the fan intake itself, because obviously the duct is going to narrow down to the fan intake, might be up at 30 meters a second. So there's quite a big area change. And so what you need to look at is our change in static pressure is obviously going to be substantial, because what's happening, of course, is that static pressure has been converted into dynamic pressure, i.e. as the flow is accelerating, there's a pressure loss to do that. And so if you want to do the calculation, there's your half rho V squared, and it's obviously V2 squared minus V1 squared. So you've got 30 squared minus 2 squared, so you can see that that number becomes quite substantial. And so for this particular example, we're talking 515 pascals. Now you might ask, well, you know, so what? Well, here's the point. If you've measured your pressure at your filter intake and you're assuming that is your suction pressure, what you'll actually find is the suction pressure at the intake to the fan itself, i.e. at the throat of the impeller. Let's say you measured your suction pressure after your filter bank of sort of say minus 200. What you'll actually find is that pressure is going to be closer to probably minus 800, because not only have you got the acceleration effect, you're going to have some losses associated with the constriction in the duct as well. So it would be quite normal for that suction pressure of the fan in practice to be quite a bit larger than you first might think. And obviously it's a direct correlation to your change or acceleration in the air velocity. Now this becomes relevant when you start to do fan efficiency and performance checks, or when you're starting to size a fan. It's quite common people miss out on the fact that they allow for the fact that there's this loss across the intake to the fan. Everyone thinks that the fan intakes, pressure drop across your inlet filters might be a couple of 100 pascals, and so they add that on, and they forget about this acceleration effect that we also need to incorporate into the actual pressure loading on my fan. So this is really where you start to come into this concept of system effects. Okay, so what are they? Well, you have an individual component system curve, so like for your filter bank, for example, for your heat exchanger. Then you have your total system curve, and the system effects are responsible for the difference between these two. So you can think of these as additional losses in the system. So a special case of this, for example, is where you have a fan exit measurement. And so if you're looking at a fan exit where you might have a velocity gradient of 5 to 50 meters a second, and we've seen this on a number of applications in practice out in industry. So when you look at the difference in your dynamic pressure generated by the two flows in the duct at 5 and 50 meters a second, you can see there your half rho V squared for your 5 meters a second, it's 14 pascals, and or just over 14 pascals, whereas for your 50 meters a second your dynamic head is over 1400 pascals. Now of course the flow is going to become mixed and slow down below your 50 meters a second, but your challenge is you're not going to recover all of that dynamic head. This is part of your losses, and so this is where having good fan design in terms of your fan housing and how you manage the flow at the fan exit and control the expansion of that air can become quite important in terms of the efficiency of the system. So to give you a summary here, so we talked about our fan intake up here, our fan exit here. You've got other changes in duct geometry, entrance and exit effects. And so these are sort of the hidden losses which give us our extra pressure drop for a given flow in our system. So just to remind ourselves once again, of course, we have our open system where everything's relative to atmosphere, so it's relatively straightforward to look at our pressure through our system. Then we have our closed systems where we've got, we need to be a little bit more careful, where in a plant where you've got multiple rooms or multiple zones, you might have different reference pressures, all based on your various HVAC loads in terms of how those closed systems are being pressurized and controlled. And so you need to be very careful moving from one zone to the next. Now one of the ways to get around this, of course, is to use an absolute pressure reading, as we've discussed previously. However, as we highlighted, if you do this, you're then going to also need to ensure that you compensate for any changes in height through the process. And so this is where, depending on the nature of the process, it could be substantial or trivial. So obviously your reference changes could also run laterally in terms of height if you're using an absolute reference frame. So closed systems obviously provide some challenges. However, we can be sensible, and as we mentioned, you can use an absolute pressure gauge. You do need to be careful. Generally, if you get a good quality gauge, you can get a resolution of sort of 10, 20 pascals, which for most industrial applications is more than sufficient. However, as we said, it doesn't take very much height to generate 20 pascals. And if you do the math in reverse, okay, if we take our density of our 1.15, okay, and then we divide by 9.81, okay, 20 pascals is only 1.7, 1.8 meters. So effectively, for those of you on the old school numbers, every 6 feet of height is 20 pascals in pressure. So so it can become, obviously that depends on the temperature that you're at, but notionally, you're sort of 10 pascals is roughly, give or take, a meter. 20 pascals, nearly 2 meters in height. So if you want to just sort of a rough rule of thumb, and so you can see that if you're measuring down to 10, 20 pascal differences, you know, a few meters here and there can actually start to impact on the relative accuracy of your measurements if you're using an absolute pressure gauge. Now, moving on from this to the supply side of the system, if you start to measure power in terms of electricity consumption, you need to be mindful of, well, what are we actually measuring? If we are just measuring fan amps, we are going to be very careful in terms of accuracy, and we'll talk about why in a minute. If you're making assumptions about voltage, often voltage isn't always measured because it can be a little bit tricky to do so. If you're not measuring voltage, you're certainly not measuring power factor. Now, I'll point out here, if you're not measuring power factor and the site's fitted with power factor correction, doesn't mean that your power factor down at the motor is 1. All that means is back at your MCC, you've got power factor correction so that the grid or the network that you're hooked up to is seeing your power factor at 1. And so just because you've got power factor correction does not mean your power factor at your motor is 1. It will vary, and it's going to vary dramatically depending on the load on that motor. So ultimately, if you're going to be looking at the system, our strong recommendation is you always look at measuring actual power. Then of course what you're looking at is, well, you've got the load on the motor versus a load on a VSD. And so you need to be careful. So just a reminder, of course, for a 3-phase motor, your power is going to be your RMS voltage times your current times √3 times cos phi being your power factor. Now, what we want to do is, well, let's consider for a minute what the errors are. So here's our equation up the top there. If we look first of all at voltage, now voltage in practice could vary depending on where we are in the country. It could be as low as 360, could be as high as 415. Now if we assume 400 volts, at 360 volts our error could be under 10%, or at 415 we're over 3, nearly 4%. So when we're assuming voltage, we leave ourselves open, but plus or minus 10%, you might be prepared to tolerate. That's probably not the end of the world. But at least you should be wary of that, and if nothing else, you can get a spot measurement to at least recalibrate your calculations and assumptions. However, now if we look at power factor for a minute, a typical number that people assume is probably about 0.85, which is probably quite reasonable. If it's a really good motor, you might be up at 0.9, but that's probably about as good as it's going to get. Now, in practice, depending on the load of the motor, it could be as low as 0.4, 0.6, 0.7, or up as high as 0.9. So if we've assumed 0.85, our error actually is 112% at the low end, i.e. we're going to overestimate our power consumption, and therefore if we're talking about reducing a load, we're going to overestimate our savings. And then on the high side, we could be under. So obviously power factor has a big range in which it can impact the accuracy of our measurements, so we need to be particularly careful. You need to understand what your power factor on your motor is. Now typically those low power factors, if you've got them, that will be where you've got a very low load. So for example, if you've got a 300 kilowatt motor and it's only loaded at sort of 100 odd kilowatts, you're going to have a power factor between 0.4 and 0.5. You're not going to be up at 0.85. It's just a nature of the load on the motor. So generally that's going to be a particular issue if you've got motors that are oversized and are being heavily or significantly underloaded. So the lesson to take home here is your actual power measurement. If you're making various assumptions, you could be overestimating by up to 120% or underestimating by 20%. So if you're doing your savings figures and all the rest of it in terms of looking at what you're doing and what you could possibly deliver, you need to be mindful that that there's some significant errors in some of your assumptions if you're not careful. So fan efficiency, well, to measure fan efficiency, it's obviously a function of our pressure rise and our volume flow rate over the fan power. Now, to be fair, this is where the pressure rise, which is the pressure rise from the fan, from the suction side to the discharge side. We need to be particularly careful in measuring that pressure as we just talked through, especially on the intake side where you've got a significant contraction and flow. Are you fully capturing that figure? If you're not, it's a relatively straightforward calculation as we went through today to be able to correct that figure and approximate it. Our volume flow rate is going to come back to how we measure that, and then obviously our fan power. But ultimately we can get a fan efficiency. Now the key thing to point out here is that we have other efficiencies in the mix. We have a motor efficiency, a drivetrain efficiency. We might have electrical losses across our VSDs, cables and the like. not to be confused with our aerodynamic efficiency of the fan. Now, when you actually see a fan efficiency on a fan curve, that will be specifically the aerodynamic efficiency of the impeller, which is going to be basically an assumption of shaft power delivered to the fan itself, which is obviously going to be your motor power consumption less all your efficiencies of your drivetrain, motor, VSD, etc., depending on where you've measured your power input. So very, very important that you understand the different aspects of the efficiency, not just assume a fan efficiency from the manufacturer off a fan curve. That is literally an assumed efficiency based on the shaft power delivered at the impeller, and of course that's assuming an ideal inlet and exit condition of the fan, which, as we've discussed, in most cases doesn't normally occur. Okay, so if we're going to take effective measurements, we need to be mindful of getting the right data, and ultimately the key point there is attention to detail. We want to be careful developing our business case and looking at the opportunities. We might need to get some help. If we're going to be successful, the reality is we need to take the systems approach, and a total systems, you need to think about who are the key people we need to engage, who's going to own it, and how do we get them engaged. Okay, ultimately, who's going to take over when you walk out the gate. Now, from a data analysis point of view, we talked about this briefly at the beginning. This is where you need to make sure that you're getting all of the relevant data that you need. Have you got the right benchmarks? And from a transients and data interpretation point of view, what do you need to consider in terms of daily and seasonal variation? Okay, so remembering that we've got a demand aspect, a distribution, and a supply aspect to consider. Now, errors, well, we've talked about the errors. We've got errors in our measurements. We've got errors in our analysis. We're going to make various assumptions. Okay, are we reflecting the true operational envelope of the plant? And then, of course, this is all going to be tied back to production or output. Okay, so we need to think through how we're going to account for these variations and understand the limitations of what we're doing. So obviously we then need to manage risk, and so obviously we need to be conservative. Are the savings identified realistic, measurable, attainable? Coming back to the importance when we're talking power savings and justifying what we're doing, we need to make sure that we've got the appropriate measurements with the appropriate degree of accuracy. Now, we're going to have acceptable system losses, and obviously we need to make some allowances for system maintenance, and we need some backup or redundancy, and so all of these things become an important point. Obviously, if our fan is right on the limit, then if the fan is one of our control variables, then ultimately our plant or process isn't necessarily going to be in control. So what are the actual limits that we need to put on the system so we're still maintaining the control that we need? So then there's a human dimension to this. There are people involved, workloads and attitudes and cultures, but ultimately the key thing I want to focus on is getting the buy-in or engagement at the appropriate level. So depending on what part of the business you sit in, you're going to have other masters that you need to get on board to support getting a change that you need, whether it's management, operations, technical, maintenance. Now, you could sit in any one of those pillars, but ultimately I can certainly recommend and attest today that the fact that if you're really going to be successful in making a change and making a difference, it's better to have these guys on board. Now, if you're going to do that, the key questions that you need to be asking are what are their needs and what are their risks? What are the things that are going to put their concerns that are going to prevent them from wanting to support making a change? And in actual fact, what you're looking for is the win-win, where what is it that can deliver what you need versus how does it also help them? How does it also lower their risk profile? Funnily enough, people don't like someone else putting in jeopardy what they're currently doing. So it's all about the win-win. And it's like all things in life. Stephen Covey put it best in his 7 Habits for Highly Effective People. If you don't have a win-win, things aren't going to last very long and they're not going to go too far. If you have a win-win, then you're halfway there to getting things done. So in life, it pays to look for an opportunity where everyone can win, as opposed to there being winners and losers. So obviously we need to be specific, we need to get the data to support our recommendation, and obviously the whole essence of today is making sure that we get the right data so that we can then do a sensible cost-benefit analysis. Key thing is just remember, we want to be conservative, we don't want to overpromise and underdeliver. So we need to close the loop in terms of reporting and be able to communicate and follow up and ensure that we've delivered what we want. Okay, now to finish off today, we've got a couple more minutes, and I just wanted to go through a couple of very quick case studies or examples. And so here's one with an industrial air heater. We will go back briefly. So you've got a fan sitting here. It's very hard to see. So you've got a diffuser expanding air out to go through a coil, and then obviously that's then going into a drying process. Now, what's interesting here is a close-up of a particular fan. Here's the air heater, and so your steam coils are sitting here and behind where this picture is. Now, what you'll notice here is this graph is actually the exit velocity profile coming out of the fan, and you'll see at the top we've got a fairly high velocity of over 30 meters a second, whereas down in this bottom corner we're sort of under 10 and sort of pushing 5 meters a second. So we have quite a maldistribution of flow, and of course our challenge is how do we get that flow to go where it needs to go. Now, what's interesting in this particular scenario, because of the duct geometry, we've got a flat duct that then takes off this way. What actually happens here is the flow separates at this point, and we get a big recirculation or dead zone. Excuse me. In the top part of this diffuser, and by and large the majority of the flow coming out of the fan ends up going through the bottom half of the heat exchanger. Now, of course, this compromises system capacity and performance. And in this particular application, the heat exchanger were two separate heat exchangers split in the middle. So obviously with the correct flow correction, you can get flow spread all the way across, and you can manage things, improve your static pressure recovery and so forth. So this is sort of an indication of the flow straighteners that were incorporated to redirect the flow to where it needed to go. Now, ultimately in this case study, what did it deliver? Well, we had a reduced static pressure drop as a combination of having a lower pressure drop across the heat exchanger coils, okay, which enabled us to increase flow for the plant, so we had a production increase. We also were able to get better static pressure recovery by controlling the expansion of that high velocity air. We had better life out of the heat exchanger coils because we had our heat load distributed through the coils appropriately. Meant startup and shutdown was a lot more effective. And in this particular application, we had a substantial reduction in steam juice because of the way the heater was configured. Now, as a little side example for today, I want to share a little bit of a different tack here, and this is a HVAC example. And so what it was actually two process plants that were joined together, and obviously a number of common openings between the two plants. Now, of course, the plants had separate HVAC systems, okay, and what was interesting is plant 1, shown in red, had a negative building pressure, supposedly, as indicated by its pressure transducer down here in the bottom corner. And what was interesting, of course, plant 2, whose reference pressure to control the HVAC system was actually in the top corner on the diagonally opposite part of the site, was showing positive. But interestingly enough, there was a substantial flow of air from plant 1 to plant 2 at the basement level. Now, what was interesting, of course, at the upper levels, there was negligible flow between the plants. And so this was sort of a bit of an anomaly. It didn't make a lot of sense, but there was a concern because obviously being a ventilated plant, they were needing that ventilation from a product and process quality point of view to actually be in positive pressure. And so the challenge was, of course, we needed to establish what was actually going on. And so step 1 was actually to verify the static pressures through the building. And what was actually discovered, if we go back to the page here, is this reference pressure here was not actually referencing the outside ambient air. it had been corrupted, it had been misconnected to another point, which meant that the pressure in that building actually was reading quite a bit higher than what was actually quite a lot higher than what was being read on the gauge. Now the consequence of that, of course, is the control system for the HVAC system was ramping the system to full load, trying to compensate and pressurize the building. However, what was actually transpiring was the building was being significantly overpressurized. Now obviously we're able to verify this by going through the building room by room, level by level. We're able to get the correct absolute pressures, then obviously compensating for height, because obviously height was an issue, especially with the two reference pressures, and we're able to realign the control systems, okay, and at the same time we're able to also identify as part of this process several localized air distribution problems that were able to be addressed. And so what was the lesson learned from this case study? Well, number one, your HVAC system can represent energy savings at very little to no capital cost. Number two, I haven't actually got it up there, but more importantly, where this can become a product quality or product safety, or certainly a plant reliability problem, you need to be very careful to ensure that the basics, often the HVAC system's forgotten about in an industrial plant. It's kind of funny how in an office building people complain very quickly when the HVAC's not working. Now people in an office building might beg to differ and argue that it's hard to get people to fix the problem, but generally in a process application it can be a little bit more dramatic in terms of the impact it can have. So just running through the numbers in this particular scenario to give you an idea of the sense of scale of this particular problem. So plant 1 had 4 55 kilowatt HVAC inlet fans. Plant 2, there were two 250 kilowatt HVAC inlet fans, and the buildings were being overpressurized to 140 pascals out above ambient instead of the design set point of 40. And so what that means is when we did the baseline power consumption, the system was drawing 450 kilowatts in total, okay, when actually once everything was corrected, it only needed to be about 360 kilowatts. Now, what does that mean in practice? Well, those of you that are astute, you'll be looking at that and saying, well, hang on, 140 versus 40, that's a massive pressure differential. It's more than 20%. Well, what you've got to understand is your HVAC system has losses across inlet filters and attenuators and the like, and so there's some suction losses on the front side, so the load on the fans isn't just the positive 140, it's also the intake losses. And so when that all comes into the mix, it actually ends up being, in this particular instance, it was 100 pascals out of 500 pascals, which is where the 20% comes from. And so what that translated to was 90 kilowatts. Now, because this is a continuous system being run year-round, what does that translate to? Well, when you multiply that 90 kilowatts by your 8,760 hours per annum, you get a substantial sum, nearly just under a gigawatt hour per annum. Now, to put that in perspective, at 10 cents a kilowatt or $100 a megawatt, that's $78,000, nearly $80,000 per annum. Never mind the extra wear and tear on everything running a lot harder than it needs to. Your pressures on your filters and everything else are a lot higher than they need to be. All of your seals on your ducts are under a lot more pressure and strain, a lot more vibration. So long term, your maintenance costs can be expected to be a little higher, or your equipment's running hotter and harder. Now what's interesting, of course, the upshot of this is actually it was very little capital. We didn't need to, but the particular plant owner of this particular installation ended up installing additional pressure transducers to have better control to prevent this sort of thing from happening in the future. So they were able to spend a little under $20,000, including all of that plus a few hours labour to sort the problem out, and hey presto, they've got an $80,000 a year saving for under $20,000. You know, the CapEx writes itself. So really, just a reminder, don't ignore your HVAC systems. I could give you countless examples of process plants with HVAC systems that are exactly like this, of various shapes and forms, where it's an easy 5, 10, 15, 20, in some cases even more percent savings, and not uncommon to sort of be in the 40 to 80 to $100,000 per annum in power savings on bigger plants. And the irony is for those of you that have small plants, you might only have, oh, those are big fans, I might only have a 10 kilowatt fan here or a 15 kilowatt fan there. The reality is the same attention to detail, where on your small system it's just a matter of making sure that your reference set points are right, that you're not over pressurizing things, and it's an easy, quick saving with no capital required at all, and it's just literally a few minutes of your time to go and have a look, scratch the surface and see what you find. So a reminder, once again, indicators of inefficient systems. You've got dirty filters, general cleanliness, closed flow dampers, you might have primary dampers, secondary, other things like duct transitions, where you've got duct vibration and noise levels, high static pressures. If you've got flexible socks on your ducts that are blowing right out when you push them, they're tight like a trampoline, there's a pretty good indication that we've got too much pressure in our system. Normally that'll ultimately lead to these socks and ducts leaking and air pouring out where you don't want it. So all very simple telltale signs. Just as you do a walk through your system, you're able to pick up there's some opportunities to take advantage of. So in summary today, ultimately we need to remind ourselves to stay focused on the whole system when we're looking at taking effective system measurements. We need to consider the absolute and specific energy consumption. And a reminder here that typically fan power, although it's a saving, is going to be fairly modest, but you'll have potentially capacity increase opportunities, reliability improvement opportunities that can ultimately help you to fund getting a change or an upgrade to your system. This is where we mentioned today, understanding the other stakeholders across your company, your organization. How can they benefit? What are their needs? And what are their risks, and how can what you're proposing also help address those needs and lower their risks? So always stop and think what else may change. So be very careful with coupled systems. You may need to allow to retune them. Indirect measurement of process variables may help you to get a better handle on flow rates and the like, as opposed to doing a fairly complicated flow rate calculation, especially where you've got some system dynamics that it's too hard to capture in one go. You might be able to look at some other process variable and capture that dynamic and be able to infer from that what your process flows actually are. Static pressure is a very effective indicator of the system efficiency, and as we've highlighted, it's very important to also compensate those measurements to allow for your changes in duct geometry where flows are being accelerated or decelerated. Also in terms of losses across intakes and exits, especially where you've got sudden expansions and contractions. And ultimately you always want to be checking and evaluating your fan efficiency. Is it running where it should be? It might be that it needs a service. Is the inlet cone and the like got the right clearances and tolerances? Other aspects of the impeller, there could be a damage there that's compromising its performance. So in summary, there's plenty of opportunities, and it all comes back to good data. Okay, so moving ahead to the future, in 2 weeks' time we have our industrial boiler corrosion and deposition failures with David Addison from thermal chemistry. Then there will be additional webinars coming in July and August. We'll be announcing those topics, and invites will be available shortly in the next week or two. Now, if any of you out there are interested in a particular topic that we haven't covered yet, or an interest in terms of a particular case study, you're certainly welcome to email those through, and we can take that on board and look to see how we can incorporate those into the program. Now, for those of you that are looking for some further help today in terms of where to from here, obviously there's some great resources under the ECA website. Your ECA account manager may be of use. You can go to our website for future webinars, registration links, and obviously a reminder that the webinars today will be available on the ECA Business YouTube channel. Now, for some fan system specific helps and performance, there's a number of useful guides. There's the DOE fan sourcebook, which is available off the web as a free download from the Department of Energy in the US. There's also a number of other documents like the fan performance document there by Mark Stevens, which is AMCA International. So yeah, there's a number of references out there that can be useful. I'm happy to answer any questions that some of you might have, so I'm happy to stay on the line for a few minutes. I can see that that we don't have any questions at the moment, but if you want to take a few minutes and punch a question in, I will stay on the line. Otherwise, thank you for joining the webinar today, and we will see you in 2 weeks' time.